say yes, that we are indeed live. There is a kitty cat here kissing me, and there is a me who is also doing something. I don't know what yet. I will put that button on, and sometimes I do these accents that I don't even know where they come from. Let me look for my other device. If I can find it, then I will share the live. Hello, hello, hello. Welcome, welcome, welcome. Welcome to the live. Welcome to the live. Welcome to the live. I have these earrings on. I have a black dress on so that I can talk to you about black holes today from Stephen Hawking's book, A Brief History of Time, where we have been covering elementary particles and the forces of nature. And then now we're on chapter 6, black holes. Hello, Reese, how are you? Reese is saying honey wine. I am drinking the honey wine on Sunday, actually, because I'm meeting a friend on that day at the place, at the Ethiopian. So currently I just have the water with me, and but that is, I'm high enough. I'm high enough from the swimming. So I think we're good. This is my black dress for the black holes class that we are about to embark on. And I need to share the live. If you could share the live, that would be great. I am okay. How's you? I am, as you see, I am here. I am pretty good, I think. I will be talking about black holes today, but first I will chit chat like normal. I just did my swimming, so I feel like I'm pretty good, like high on the endorphins and the hormones or the chemicals from that. On Sunday, I will do honey wine. I know I promised honey wine today, but I can only afford to eat out once a week at this Ethiopian place where it costs $20 to eat. It's very nice. It's very, very nice. Very nice. How are you? How is everyone? And if you're seeing this as a video upload later on, thank you for joining. Thank you for watching. Thank you for commenting. Thank you for liking. Can we get 20 likes? Reese, where were you last night? We looked and we looked, and we did not find you. We looked and we looked. Doro was quite aggrieved. Quite aggrieved. He knew not what to do with himself because you were not here. You weren't. Thank you for liking the live. Can you please like the live, Reese, and whoever the second person is? Thank you so much. Thank you for liking the live. Thank you, thank you, thank you. I woke up and the stream was just ending. Aww. Hi, Finlay. Hello, Reese. Hello, Finley. Hello, everybody. I did like the live. Thank you, thank you, thank you, thank you, thank you, thank you. Please do like the live. Can we get 10 likes? Can we get 20 likes? Thank you, thank you, thank you, thank you, thank you, thank you. Can you show me how to do jumping jacks? Indeed, I cannot, and I'm wearing a dress, so indeed, I will not. Rickman. Oh no, Fuji. Fuji Baba is crying. Fuji. Scooby-Dooby-Doo, where are you? Fuji, Mama's here on a live. I did like the live. Can you show me how to do jumping jacks? Finley, I hear you loud and clear, but indeed I cannot. I do not have the flexibility for a jumping jack or a Jane. Done like, thank you so much, Rickman Mix Vlog. Rickman, thank you so much. Thank you indeed. Thank you, much appreciate you. Watching from Philippines, welcome, welcome, Philippines, I love it. Philippines, thank you, welcome, 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 hello, 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 hi, 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 hello, hello, hello. Welcome to my live. I am wearing black for the black holes that we will cover today after we chit chat and say hi to everybody that is feeling like saying hi in the chat. Hello, Imamullah Asif. Hi, hi, how are you? You're very welcome, gorgeous. Oh, thank you, thank you. Some people say that is my middle name. Thank you, thank you. Fuji. Fuji Baba, Mama's here. Oh, Fuji, oh, Fuji. Oh, Fuji was crying lots and lots, lots and lots. Hi, Fuji, baby. Mama loves you the best of all. Hello, call me Sat. Hello, Imam. Let me say hi to everybody. I think Reese is saying hi to somebody. Hello, Test Europe. Hello, Rickman. Hello, Imam. Hello, Test Europe. Hello, Call Me Sati. Hello, Rickman Mix Vlog again. Hello, how are you? How are you? Rickman, are you the one from Philippines? Did I get that right? And let me have some water while I look at you. Look at your comments. Reese, okay, Lang, how about you? How are you? Look at you guys. So on this chat, a lot of people find that they make friends with each other, and a lot of people find that they indeed find the community of their life that they have been looking for. So you might want to like, share, and subscribe. In fact, you should share this with every family member, with every friend, with every co-worker, and make your life go from exciting to even more exciting. And prepare to learn about black holes from the very, very, very extraordinary, just a standout physicist, Stephen Hawking, and his book. Imam, thank you for the emoji. Hello. Hello. Do you guys like my black dress for the black holes? I forgot I had this dress and my golden necklace. No, not necklace. What is this? An earring with the black dress. Do you like it? It is for the live that I put it on. Okay. Okay. I'll settle down. Don't worry. You're so high on life right now. I am. The gym does that. I am. I love it. I love it. And the gym closes early on Fridays. So here I am. I am ready for the live. Can you please like the live? If you're joining, could you please like the live? I see only 2 likes and I'm quite disappointed. Can we get 10 likes? Can we get 20 likes? Reese, can you write like and subscribe on your comments? And I'll pin it. Oh, and Reese, how's your girlfriend? Or boyfriend? How are they? Say something. Share something. Thank you for the emojis. Thank you, thank you. Hello, Imam. Did you like the live, Imam? Ullah, Asif. I love the name. It's very beautiful. Please like and subscribe the stream. Yes. There we go. Now I can... Well, I don't want to assume. You guys like James so much. I don't want to assume anything. I don't assume. It could be girlfriend, boyfriend, them friend. I don't know. Where is my friend Dora? Imam sends XXX. Thank you, thank you. Hugs back to you, Imam. Hello, hello, hello. Okay, I pinned it. Please like and subscribe. Thank you, thank you, thank you, thank you, thank you, thank you. Actually, where is Ver? You're not a they, them? Pink eyes? What do you mean? Hello, ads. Honey, be careful. I am not sure what you're trying to say, ads, but put as in could. Could you please like the live? Oh, Imam is saying, naam kya hai? Naam kya hai? Are you asking my naam? Imam, you have to stick around. I think you will find out my naam beyond the naam that is Baji the handsome cat. I'm Baji the handsome cat's mother. Pure, direct mother. Direct mother. Mummy hu Baji ki. Mummy who made. Okay, let me now share the live. Hold on. Hang on. Let me share the live because I've forgotten to do that as per usual. And then I will start the topic of today, black holes. So now let me remind you as I do this that we have been talking about elementary particles and the forces of nature. So we talked about both matter particles as well as force particles. So forces are carried also by certain particles, and we talked about that. So indeed, we talked about leptons, quarks, and bosons, and these bosons were basically the force carriers, and the interactions between various types of particles were happening through these bosons. And depending on the type of interaction, it would be a different type of boson. So for example, we talked about how the electromagnetic interaction is carried by photons, which is a type of boson, and it happens to be a massless type of boson, photons. And then we also talked about how the weak nuclear force saw some sort of unification with the electromagnetic force, and that particular type of force or type of interaction between, for example, neutrinos, etc. excuse me, is carried by certain other types of bosons, and these were the W plus, W minus, and the Z naught type of bosons. Again, these bosons, though, had a different mass. They were more massive, meaning that the force carried by them could not be as long range as the force carried by the massless photons in the case of electromagnetic force. Hello, Ace Wolf Peach. So we named and we talked about certain interactions like the ones I just said, electromagnetic force, the weak nuclear force, strong nuclear force, and of course the gravitational force. These 4 types of fundamental forces of nature, as well as the particles involved that carry those forces, as well as the particles that interact with each other, the matter particles that are sort of undergoing these forces. And hello, soon-to-be wife of who? And we also talked about how is there sort of a regime, an energy regime at which these forces might have some sort of unification. Maybe there is a grand unified theory, or a GUT, which basically unifies the electromagnetic force with the weak nuclear force and with the strong nuclear force. Maybe those 3 types of forces have some sort of unification at a higher energy regime, or some spectacular specific energy scales at which maybe those have some sort of unification. Maybe we're sort of seeing the same kind of interaction play out, but at different energy scales. And we did see that there was some sort of unification, but then Stephen Hawking noted that this GUT, this grand unification theory, that so-called grand unification theory, in terms of these 3 forces sort of being unified, is not all that grand, because to really be the grand unification theory, you'd have to include gravitation as some sort of unification as well. Some sort of explanation of gravitation would have to be coherent with the rest of these 3 things. And also, remember that when Einstein was trying to work on the GUT of his time, grand unification theory as seen by Einstein, he was actually trying to unify all of relativity with quantum mechanics, with electromagnetism, with everything. So it would really be a theory, the ultimate grand unified theory would really be a theory that explains all of it, all of the things in the universe, and especially it would have to explain everything that we have learned from quantum mechanics as well, even though quantum mechanics is kind of bizarre and has some specific and bizarre properties of these particles that we have seen, such as spin and etc. So quite a bit has been learned about the universe, about the nature, through quantum mechanics and the scales of quantum mechanics, which is of course the very tiny scale of a particle scale, subatomic scale, right? Some of these particles we're mentioning are really quite small. Like lepton, an example of a lepton is an electron, which is of course inside the atom and sort of orbiting the nucleus. An example of the next type of particle family, quarks, is very tiny. They exist within a proton or a neutron. Protons and neutrons are made up of quarks. And then the last type of particle family, boson, is things like photons, W plus, W minus, Z naught, and other things such as maybe the graviton, if we found the graviton, or Higgs boson, those types of things. So basically, this the elementary particles, or the standard model of particle physics, comes from the success of quantum mechanics, if you will. If quantum mechanics was not successful and it had been killed earlier on in the 20th century, then we would not see it sort of thriving and thriving and thriving and thriving beyond what it was able to do in the 1920s, let's say, and keep on going until we see it really thriving towards the end of the 20th century, and more particles being discovered and particle physics coming out of it. So that's why we talked about, Stephen Hawking wrote a whole chapter on particle physics, pretty much. Actually, a couple of chapters, because he had the uncertainty principle chapter that we covered a couple of days ago. That's really sort of an introduction to quantum mechanics for you. And then the next chapter, elementary particles and the forces of nature, is really, in a nutshell, particle physics, which would not have developed if quantum mechanics had not been allowed to thrive. Doro, hello. Thank you so much for joining. Thank you so much for being here and liking the live. 5-hour water break. You mean hour? So this is sort of to kind of bring together all of the things really in the universe. So on the one side, we have general theory of relativity giving us an updated theory of gravitation and telling us a lot about the universe and how it works. And then on the other hand, we have quantum mechanics and its developments, which gave us particle physics, which is also extremely important. And together, we might learn more. And if you're really trying to unify everything, you would find a way to subsume general theory of relativity and quantum mechanics at the least, because these two theories sort of don't always agree. And certain things are kind of missing in general theory of relativity, and certain things are kind of missing, or at least very bizarre, in quantum mechanics. If you talk to a true quantum mechanics advocate, they might not agree that it's incomplete, but they will probably agree that it is kind of bizarre. The uncertainty principle, the probabilistic nature of it, were things that people really struggled to accept when it was first kind of coming out. But at the same time, even though people struggle to accept these things, they very much hold true even to this day. Because if they didn't, we would not have Aapka number kya hai? Somebody asked. She's already married to a microwave. That is true. There is a microwave that I'm quite committed to. So basically, all of that is to say that there's some drama in quantum mechanics, but it survives, it thrives, and it gave rise to particle physics, which I think was difficult for a lot of people to accept, but it thrives. And we talked a bunch about that for the last couple lives when we covered that chapter, Elementary Particles and Forces of Nature. That's basically particle physics. So now, now, that's true. You missed a massive 4-hour water break. So now we will talk about black holes. Now, as you know, black hole is another example of a singularity. The Big Bang, which is theorized to be the beginning of the universe, is a type of singularity. But there is another type of singularity, and this is black holes. So the fact that general theory of relativity might not fully explain these singularities is sort of a flaw of it. It doesn't have to, but we should think about it. And I think Stephen Hawking did, and he worked on, among other things. This was one of the biggest. This was one of the biggest things that he worked on. And specifically, he worked on black holes. So we will take a look at what he did and what he found, because keep in mind, we are talking about brief history of time in the context of course, the universe, where basically he's saying that time as a concept would have started when the universe started. So really, we're talking about the Big Bang. The Big Bang started off the universe. That is where the concept of time comes in. That's where tick tock starts. And from before that, it doesn't make sense to really think about time unless you have some other reason for thinking about time, such as religious reasons or spiritual reasons. But the Big Bang is a singularity. But it is not the only singularity. The other singularity of nature that we know and love is, of course, black holes. So we will talk about that, and we will see what he has to say about that. Stephen Hawking here, Brief History of Time from his book. Bat Shit Karezi says, are you engineering? I am not engineering. I did physics, pure sciences. No, I did not do engineering. So, yeah, just want Andrew to talk about the long water breaks. Oh, you want the long water breaks conversed upon? Aw. Well, I was happy to see that everybody was catching up with each other during the break before bed. That was very nice of you all. Thank you so much. Can we get 20 likes? I like that everybody made friends with each other. Aww. Chickpea break. Hello. Hello, Ver. All right. Now we will talk about black holes. Specialty is in particle astrophysics. Ver, welcome to the mod fam. Yes. My specialty is in particle astrophysics within physics with the subspecialty is neutrinos with RF techniques. Thanks, Reese. We missed you last night. Okay. The term black hole is of very recent origin. It was coined in 1969 by the American scientist John Wheeler as a graphic description of an idea that goes back at least 200 years to a time when there were two theories about light. One, which Newton favored, was that it was composed of particles. The other was that it was made of waves. We now know that really both theories are correct. By the wave-particle duality of quantum mechanics, light can be regarded as both a wave and a particle. Under the theory that light is made up of waves, it was not clear how it would respond to gravity, but if light is composed of particles, one might expect them to be affected by gravity in the same way that cannonballs, rockets, and planets are. Pretty nice. At first, people thought that particles of light traveled infinitely fast, so gravity would not have been able to slow them down. But the discovery by Roemer, that is R-O-E-M-E-R, Roemer, that light travels at a finite speed meant that gravity might have an important effect. Thank you. Thank you, Ver. Thank you so much. On this assumption, a Cambridge Don, John Mitchell, wrote a paper in 1783 in the Philosophical Transactions of the Royal Society of London, in which he pointed out that a star that was sufficiently massive and compact would have such a strong gravitational field that light could not escape. Any light emitted from the surface of the star would be dragged by the star's gravitational attraction before it could get very far. Mitchell suggested that there might be a large number of stars like this, although we would not be able to see them because the light from them would not reach us. we would still feel their gravitational attraction. Time is relative, indeed. Such objects are what we now call black holes because that is what they are, black voids in space. Hello, Rose Dawson. A similar suggestion was made a few years later by the French scientist, the Marquis de Laplace. You know Laplace, right? Apparently independently of Mitchell. Interestingly enough, Laplace included it in only the first and second editions of his book, The System of the World, and left it out of later editions. Perhaps he decided that it was a crazy idea. Also, the particle theory of light went out of favor during the 19th century. It seemed that everything could be explained by the wave theory. So, right, there was a lot of development in electromagnetism, which is the wave theory of light, with all those people, Faraday, Maxwell. They contributed immensely to, of course, the electromagnetic theory. And in that theory, the speed of light was a constant, and it just kind of falls out as a constant of nature. The speed of light in vacuum, that is. And so all this like wave theory of light really kind of took over. So in the 19th century, which would be the 1800s, light was basically more a wave than anything else, whereas really in the 20th century, it started to have a particle nature in our understanding, like, you know, photoelectric effect. The old quantum mechanics was really literally Einstein and others contributing to the particle nature of light, along with the wave nature of light. Chat is slow again. We need some action. Go ahead, guys. I'm loving it. Bring out the chickpeas. That's true. I might actually make chickpeas in a little bit, but let's do a little bit more reading and studying first. Thank you so much. Thank you so much for being here. If you want the chat to be more active, you should share the live with every relative and friend and coworker. Harper! We need singing and shit. Hi, Harper. Hello. So let's keep going for a little bit, and then we will have singing and chickpeas. Okay. Give me a moment. Also, the particle theory of light went out of favor during the 19th century. It seemed that everything could be explained by the wave theory, and according to the wave theory, it was not clear that light would be affected by gravity at all. Yes. In fact, it is not really consistent to treat light like cannonballs in Newton's theory of gravity, because the speed of light is fixed. A cannonball fired upward from the earth will be slowed down by gravity and will eventually stop and fall back. A photon, however, must continue upward at a constant speed. How then can Newtonian gravity affect light? That's a very good question. Does it affect light? Does anything happen with light in Newtonian gravity? Thank you. A consistent theory of how gravity affects light did not come along until Einstein proposed general relativity in 1915. So this updated theory of gravitation was very much needed in order to understand the effect of gravity on light, because as far as Newtonian mechanics goes, I mean, you can't really affect light. Light has a constant speed. The speed of light in vacuum is a constant of nature. So it will always travel at that speed in vacuum. And so as far as Newtonian mechanics goes, things with mass accelerate under gravitation, etc., etc. So the picture of how light is affected by gravitation is really not, doesn't really come together until Einstein worked on his general theory of relativity. Even the special theory of relativity was not really enough, because it is something that holds true for inertial frames of reference when things are moving at a constant speed, in other words. So if you're under some kind of acceleration, then it doesn't really hold true anymore. And he knew that he would have to work on a more general theory of relativity in order to explain more general things. So electric and magnetic fields oscillating and turning into each other is light. You can elaborate on your question further, but electric and magnetic fields oscillating is light. The wave nature of light comes from that. Thank you for so electric waves can go like this, magnetic waves can go like this, and then the wave that we get from that in the transverse direction is light. Okay. As in, the electromagnetic theory is the wave theory of light. Okay? Okay, so we're coming to the point where we are oh yes, yeah. That's a changing magnetic field creating an electric field and vice versa. Those are the interactions of electric and magnetic fields. They do affect each other. That is the whole electromagnetic theory. And basically the electromagnetic theory, when you get the fuller insight on it, you realize that, oh my gosh, treating electric and magnetic fields separately is kind of silly. And really, special theory of relativity kind of gives us a way to treat it more generally. And we get light. And then we have light. It's quite beautiful. So, but yeah, you're correct. That is all good. That's just electric and magnetic fields affecting each other. And then when we have electric and magnetic fields oscillating through vacuum, then we get light. That's the wave nature of light. Remember how we talked about how people were like, light is a wave, so what is it? What is waving, right? What is waving? Is it ether? Is it some other medium? Like, for example, sound waves go through a medium like air or something else, right? Light waves, the thing that's waving is electric and magnetic fields. And just that can happen in vacuum or other medium or other media. So, okay, we'll keep going. A consistent theory of how gravity, but we know, because we covered particle physics in the last live and we just kind of saw that, we know that light is photons. The particle nature of light is photons, which is massless. So here comes the question of how is gravity affecting light? What does light do under gravitation? This is a very important question in the universe, because can anything bend light? Does light sort of change based on gravitation at all or anything like that? That is to be discussed now, I hope, I believe. And we needed Einstein's theory of general relativity and how he basically gave us gravitation as a curvature of space-time. We needed that, which is an updated theory for gravitation beyond Newtonian mechanics. We needed that to fully understand the effect of gravitation on light. Okay? Okay, so a consistent theory of gravity affects light, of how gravity affects light, did not come along until Einstein proposed general relativity in 1915, and even then it was a long time before the implications of the theory for massive stars were understood. To understand how a black hole might be formed, we first need an understanding of the life cycle of a star. So this is going to be a little bit of review because we have talked about how certain stars, when they die, they become black holes. Other ones will become white dwarfs or neutron stars. So we've kind of talked about how stars go through their life cycle and such. So this will be like a little bit of review, but let's look at it from Stephen Hawking's point of view. The reason why what is a wave versus what is a field might be a little confusing is because I didn't really write it down for you in mathematical form. One of these days I should do the math for you on a whiteboard, and then it might be more clear. A field is different than a wave, but since you ask here, that tells me that I think a mathematical visit of field and wave would be necessary here. So yeah, electric field, magnetic field, when those fields oscillate through space in a certain way, gives rise to something more, which is the wave, which is in this case light wave. So I can write down, let's see, let me see if I can, think of a quick way to explain it. So a field, do you know what vectors are by chance? So there's a math way of defining everything. I think it would be good for me to go through the math way of defining everything because electromagnetism is a very mathematical theory. So I think without that math, that's not true. Without the math, it's difficult. But basically, there's a mathematical way and then there's a drawing way. I think I should do both of those using a whiteboard soon. So thank you for that feedback. Let me keep going. To understand how a black hole might be formed, we first need an understanding of the life cycle of a star. A star is formed when a large amount of gas, mostly hydrogen, starts to collapse in on itself due to its gravitational attraction. As we know, stars can run out of nuclear power and basically collapse on itself, giving rise to their death. And some of them, the very, very massive, the most massive ones, will end up into a black hole. As it contracts, the atoms of the gas collide with each other more and more frequently, and at greater and greater speeds, the gas heats up. Eventually, the gas will be so hot that when the hydrogen atoms collide, they no longer bounce off each other, but instead coalesce to form helium. The heat released in this reaction, which is like a controlled hydrogen bomb explosion, is what makes the star shine. So we're still talking about the star's process here. So the heat released in this reaction, which is like a controlled hydrogen bomb explosion, is what makes the star shine. This additional heat also increases the pressure of the gas until it is sufficient to balance the gravitational attraction. So this additional heat also increases the pressure of the gas until it is sufficient to balance the gravitational attraction. In other words, we need the nuclear power, the nuclear reactor, which is at the center of the star. We need that going in order to counter the gravitational attraction of the star's mass and in order for the star to keep from collapsing. Otherwise, the star will collapse. And it does happen where sometimes it runs out of nuclear power and then it does collapse. And then depends on the mass of the star initially, it will collapse and end up, after certain more processes, into either a white dwarf or a neutron star or a black hole. Okay, so we'll keep going. The additional heat also increases the pressure of the gas until it is sufficient to balance the gravitational attraction. and the gas stops contracting. It is a bit like a balloon. There is a balance between the pressure of the air inside, which is trying to make the balloon expand, and the tension in the rubber, which is trying to make the balloon smaller. Stars will remain stable like this for a long time, with heat from the nuclear reactions balancing the gravitational attraction. That's how we have the sun. We can keep going. We don't have to worry about the sun collapsing anytime soon, for example. Eventually, however, the star will run out of its hydrogen and other nuclear fuels. Paradoxically, the more fuel a star starts off with, the sooner it runs out. So the more massive stars actually have spectacular deaths sooner, and they actually die out sooner. This is because the more massive the star is, the hotter it needs to be to balance its own gravitational attraction. That's a nice sentence right there. I was going to explain it, but I think he did it as well. So the more massive the star is, the hotter it needs to be to balance its gravitational attraction, its own gravitational attraction. The more massive, the more it needs to do to counter its own gravity. And the hotter it is, the faster it will use up its fuel. Our sun has probably got enough fuel for another 5,000 million years or so, but more massive stars can use up their fuel in as little as 100 million years, much less than the age of the universe. So when a star runs out of its fuel, it starts to cool off and so to contract. So literally it's starting to collapse, basically. As soon as it runs out of fuel, it will start to contract, because guess what else is going on there in the star? It's gravitation. Gravitation is an attractive force every time. Every time it's an attractive force. So it will make that star collapse. When a star starts to run out of fuel, it starts to cool off and so to contract. What might happen to it then was first understood only at the end of the 1920s. So as far as what will exactly happen, the fact that it ends up in a black hole or whatever, that wasn't really so obvious. Thank you everybody for being here. Thank you, Reese. Thank you, Doro. Thank you, Titanic. So now for the story time of this whole thing. In 1928, an Indian graduate student, Subramanian Chandrasekhar. So Chandrasekhar limit is a very famous limit that we have talked about in the past with white dwarf masses and such. We will talk about now the guy, Chandrasekhar, right here. So Subramanian Chandrasekhar set sail for England to study at Cambridge with the British astronomer Sir Arthur Eddington, who is an expert on general relativity. According to some accounts, a journalist told Eddington in the early 1920s that he had heard there were only 3 people in the world who understood general relativity. Eddington paused, then replied, "I'm trying to think who the third person is," during his voyage from India. So it would be Einstein, Eddington. I actually don't know who the third person is either. I mean, this is the first... I didn't know very well that Eddington was considered to be such a general theory or general relativity expert. But I'm also trying to think who the third person could be. Thank you, Titanic. Thank you, Doro. Thank you, Reese. During his voyage from India, Chandrasekhar worked out how big a star could be and still support itself against its own gravity after it had used up all its fuel. The idea was this: when the star becomes small, the matter particles get very near each other, and so according to the Pauli exclusion principle, they must have very different velocities. This makes them move away from each other, and so tends to make the star expand. A star can therefore maintain itself at a constant radius by balance between the attraction of gravity and the repulsion that arises from the exclusion principle, just as earlier in its life gravity was balanced by the heat. Thank you. You're not what? You're not here? Oh. Chandrasekhar realized, however, that there is a limit to the repulsion that the exclusion principle can provide. The theory of relativity limits the maximum difference in the velocities of the matter particles in the star to the speed of light. This means that when the star got sufficiently dense, the repulsion caused by the exclusion principle would be less than the attraction of gravitation. Chandrasekhar calculated that a cold star of more than about 1.5 times the mass of the sun would not be able to support itself against its own gravity. Remember the Chandrasekhar limit? Hello? Oh, is Steven not here? Where's Steven? He's usually always here. We need James. James really was funny as heck. James used to come much later at night, actually. I think it's not time yet for James to wake up and put on his clothes. Okay, so he realized that a cold star of more than about 1.5 times the mass of the sun would not be able to support itself against its own gravity. This mass is now known as the Chandrasekhar limit. A similar discovery was made about the same time by the Russian scientist Lev Davidovich Landau. This had serious implications for the ultimate fate of massive stars. If a star's mass is less than the Chandrasekhar limit, it can eventually stop contracting and settle down to a possible final state as a white dwarf. Remember, we talked about white dwarfs for the less massive stars that become white dwarfs basically when they die, with a radius of a few thousand miles and a density of hundreds of tons per cubic inch. A white dwarf is supported by the exclusion principle repulsion between the electrons in its matter. So there's basically a bunch of electrons and they have electron degeneracy pressure in order to support the white dwarf together once the star is dying and contracted and all that. Okay. Screenshot me now. Did you get it? A white dwarf is supported by the exclusion principle repulsion between the electrons and its matters. We observe a large Wait, I'm forgetting. Is Waterbreak Doro or is Waterbreak Ver? Who has too many pics of me on their phone? All the faces had to be deleted. Oh, you're Doro. So what's wrong with my pics? It is true. Having random internet girl pics is not a good thing. Especially for relationships. You should definitely delete them. But take a screenshot of this and use it if you will. Or not. Don't worry. It's true. Absolutely true. You're an internet lady. I can't do that. Especially when I settle with a GF. Good man. Good man. Good. That is correct behavior. Indeed, you must delete everything. Indeed. I bless all the deletions. All of it. Blessed by me. Can we get 10 likes? Delete everything? Okay, goodbye phone. What do you mean, goodbye phone? What did the phone do? I bless the deletions. I bless. Phone has been deleted. Tell us about the missus. The missus. I might stick an Owen's photograph on the mantelpiece and see how the missus reacts. Can you tell us more about her? We have heard nothing. How is she? Is she from Scarborough? Oh my God. Oh, sorry. Is she from Belgium? Thank you for liking the live. Can we get 20 likes? We're not getting on very well. Also, stop doxing me. I'm so sorry. I am so sorry. I feel like I've done a bad thing. Okay, thank you. Thank you so much. Can we get 20 likes? Okay, I'm gonna go back here. I feel like I was doing a great job when I was reading. And then when I started to talk to my mods, it didn't go as well. Landau pointed out that there was another possible final state for a star. Okay, actually I missed a sentence. A white dwarf is supported by the exclusion principle repulsion between the electrons and its matter. So we know that a white dwarf is held together by the electron degeneracy pressure. We observe a large number of these white dwarf stars. One of the first to be discovered is a star that is orbiting around Sirius, which is the brightest star in the night sky. So even Sirius has a white dwarf about it. Landau pointed out that there was another possible final state for a star, also with a limiting mass of about 1 or 2 times the mass of the sun, but much smaller even than a white dwarf. These stars would be supported by the exclusion principle repulsion between neutrons and protons rather than between electrons. They were therefore called neutron stars. It did work. Good thing. It did work. Yes, it worked. I see it. Between water break and look of disgust, I'll forget who is who and which is which. As it is, you guys have so many usernames. But now between chickpea, water break, and you, my next 4-hour water break. Landau pointed out that there was yet another possible final state for a star, also with a limiting mass of about 1 or 2 times the mass of the sun, but much smaller even than a white dwarf. These stars would be supported by the exclusion principle repulsion between neutrons and protons rather than between electrons. They were therefore called neutron stars. They would have a radius of only 10 miles or so and a density of hundreds of millions of tons per cubic inch. At the time they were first predicted, there was no way that neutron stars could be observed. They were not actually detected until much later. We did talk about neutron stars as well in the past, so it's kind of like review here. Stars with masses above the Chandrasekhar limit, on the other hand, have a big problem when they come to the end of their fuel. In some cases, they may explode or manage to throw off enough matter to reduce their mass below the limit and so avoid catastrophic gravitational collapse. But it was difficult to believe that this always happened, no matter how big the star. How would it know that it had to lose weight? Thank you. And even if every star managed to lose enough mass to avoid collapse, what would happen if you added more mass to a white dwarf or neutron star to take it over the limit? Would it collapse to infinite density? Eddington was shocked by that implication, and he refused to believe Chandrasekhar's result. Ooh. What would happen if you added more mass to a white dwarf or neutron star to take it over the limit? Would it collapse to infinite density? Look of disgust. Thank you, look of disgust. Thank you, water break. Thank you, Felipe. Hola, bonita. Thank you, 908VR123. Can we get 20 likes? Can we? Can we? Eddington thought it was simply not possible that a star could collapse to a point. This was the view of most scientists. Einstein himself wrote a paper in which he claimed that stars would not shrink to zero size. The hostility of other scientists, particularly Eddington, his former teacher, and the leading authority on the structure of stars, persuaded Chandrasekhar to abandon this line of work and turn instead to other problems in astronomy, such as the motion of star clusters. However, when he was awarded the Nobel Prize in 1983, it was at least in part for his early work on the limiting mass of cold stars. Hello. Hello, Sari VR. Hi. Hello. Hello. Thank you so much for being here. Can we get 20 likes? Chandrasekhar had shown that the exclusion principle could not halt the collapse of a star more massive than the Chandrasekhar limit. But the problem of understanding what would happen to such a star, according to general relativity, was first solved by a young American, Robert Oppenheimer, in 1939. His result, however, suggested that there would be no observational consequences that could be detected by the telescopes of the day. Then World War II intervened, and Oppenheimer himself became closely involved in the atom bomb project. After the war, the problem of gravitational collapse was largely forgotten, as most scientists became caught up in what happens on the scale of the atom and its nucleus. In the 1960s, however, interest in the large-scale problems of astronomy and cosmology was revived by a great increase in the number and range of astronomical observations brought about by the application of modern technology. Oppenheimer's work was then rediscovered and extended by a number of people. So yeah, we get on well most of the time, but she's like a hothead. I didn't realize that there was so much going on. That's very happening. How long have you been married? Oh, can I ask that? You don't have to say. But congratulations! The picture that we now have from Oppenheimer's work is as follows. The gravitational field of the star changes the paths of light rays in space-time from what they would have been had the star not been present. The light cones, which indicate the paths followed in space and time by flashes of light emitted from their tips, are bent slightly inward near the surface of the star. This can be seen in the bending of light from distant stars observed during an eclipse of the sun. As the star contracts, the gravitational field at its surface gets stronger and the light cones get bent inward more. Can we get 20 likes? We're not married. This can be seen in the bending of light from distant stars observed during an eclipse of the sun. As the star contracts. Water break, do you have a secret wife as well? And why aren't these wives joining my live? We need some wife in the live. I say you should bring your wives next time. In fact, ask them to join now from their phones or tablets. Why not? This is why I don't have any women, because you're not bringing your wives enough. I did on in person, on the internet. I'm required to mock her century water breaks. That's true, they're centurial. I don't. Secret wife, I'm not married. I broke up with my girlfriend and now have been experimenting, maybe one day. Oh, now experimenting with boys, girls, and them days. Batman, you should sit down. But you guys should bring just everyone legal age though. Oh good. Oh, I see. Okay. Batman, you're up to no good as usual. And I gotta go soon, by the way. But I just wanted to say one thing, which is that how dare you? What country are you from? Yeah, that's a great question. Batman, what country are you from? Given that you're filthy, it's probably the US. I feel a water break coming. Oh, did I ever share the live? Oh my God. You feel a okay. I don't know what just happened in the chat. Something about dirty. No, I meant your mouth is dirty. I meant you're filthy because you say filthy things, Batman. And you're probably from the Midwest. That's what I meant. That's what I meant. That's what I meant. That's what I meant. Okay? Okay, okay. I'm looking at over at my tablet. Okay. So, what I meant was, yeah, filthy mouth person is probably from the Midwest. But now let me get back to the other question. Oh, Andrew needs to have iPad lives. That's true. My iPad is here. My iPad is here. Oh, thank you so much for liking the live. Thank you so much. Thank you. Thank you. Please continue to like the live so that we can get 20 likes. But why you guys are not bringing your wives to this live is beyond me. You know, if you didn't say filthy, dirty things, then you could probably bring your wife to the live, and then I would have twice as many. I'm from America, Colorado. See, I knew it. You mountainous, filthy mouth. I'd never bring my wife here, though. Why? You should bring your wife so then I can have twice as many people liking my life. I would be at 20 likes already. You guys, you're wasting the wives. That's not good. That is not good. Nothing against mountains, only against your filthy mouth. Okay, I have to leave. I have to go on a water break. You guys can watch the kitty cats. I came for the physics, to be honest. I didn't see Owens for a few streams. I know, you've been missing out. Just end the live. You're hurting your channel when you do that. Aw, thank you for being so thoughtful towards me. Combat sports! I'm about to leave. I came for the physics. Aw, thank you so much. Rewind. Rewind. Combat sports. Combat sports. Go rewind. See? Water break is saying keep it on for 24 hours. Oh, that's you. I see. I've already forgotten who is saying who. Who is who? Who is saying what? Combat sports rewind. I just started black holes. But yeah, missed you if you missed the live. Okay, let me say goodnight tonight. Y'all can keep chatting for a bit. Thank you so much. Thank you, thank you. Thank you, thank you. Thank you, thank you. Thank you, thank you.